Hello and welcome to ThePrint. My name is Soumya Pillai and today we are in Delhi's India International Center where we are in conversation with Professor Priyamvada Natarajan. She's a renowned astrophysicist currently with the Yale University. She's an expert in dark matter, black holes and dark energy. And recently her discoveries on black holes have been confirmed by the James Webb Telescope. Another very big feather on her illustrious career was that she was named as one of the 100 most influential people of 2024 by the Time magazine. Welcome to ThePrint, Professor Natarajan.
Thank you very much. I'm a fan, so I'm really delighted to be talking to you.
We are a fan as well, so I think it's mutual admiration. I'm going to jump right to the questions, Professor Natarajan. Before we get into your work per se, just to set some context for our viewers, if you could just tell us, give us a little history lesson about, how far back does humanity's knowledge and interest about black holes go back to? If you could just tell us a little bit and then we'll
basically you want me to tell you the story of the universe in a nutshell, right? So essentially we have a very good understanding of how our universe came to be. We believe that it started out as a very dense and hot, and then it slowly cooled and expanded over time. And during the course of that time, the expansion of the universe was actually driven by what we believe now to be dark energy, the accelerating expansion of the universe. And that has happened in more recent times. The entire timeline of a universe is about 13.8 billion years. And so we have a full origin story. So starting from t = 0 to today. And we have pretty compelling observational evidence going back to when the universe, like direct evidence, actual signals, energy and light, from when the universe was about 380,000 years after the Big Bang. So quite far into the infant universe, we've been able to look out. And of course, some of these signals and some of this evidence, astronomical evidence, is direct imaging. Some of it is indirect inference. So that brings me to the topics that I am most excited about, sort of the invisible constituents of our universe. It turns out that dark matter and dark energy, which do not emit any light, so they do not actually present to us as visible phenomena, but they manifest, their properties manifest in the universe and we're able to infer them. So, the entire material universe that we are familiar with, the stuff that we are made of, everything in the periodic table is only 4% of the inventory of the universe, the ordinary atoms that we are made of. There is a lot more matter. That's barely 90% of the matter. So only 5% or so is the ordinary atoms. The rest of it is dark matter. We believe it's also material. We believe it's matter, and it was particles that were created in the very early universe. And we know that this dark matter actually shaped the universe, and every galaxy has a huge amount of dark matter. It's a cocoon within which the galaxy forms, within which all the visible matter actually forms stars and emit light that we see. And we also discovered as recently as 1998 that it was known from the 1920s, late 1920s, the astronomer Edwin Hubble found that the universe was expanding. And it's expanding in the sense that the distances between any two galaxies was growing with time. So people often ask me, like, what are you expanding into? We're actually not expanding into anything. The way to think about it is the distance between galaxies actually changing with time. So he discovered that in 1929. But in 1998, astronomers discovered, actually two independent teams discovered that the expansion of the universe was actually accelerating. Which means that you need to, there has to be some energy that's powering the accelerating expansion. And it turns out that's the thing we call dark energy. And so that's all we know about dark energy right now. We believe that this kind of force that was causing this accelerating expansion existed in its has been constant and it's been around from the very early times. And that it was always a tug between gravity and the sort of expansion that has shaped our universe. And we also know that this dark matter, which is the primary composition of the universe, actually deflects light. It doesn't emit light, but it deflects light. So whenever you have a lump of dark matter in the universe and you have an object like a star or galaxy behind it or a quasar that's emitting light on its own, this lump of dark matter behaves like a lens and actually focuses the light, but actually causes deviations in the path of light by deflecting light. And so that manifests in a way where you don't see objects as they really are in the background, but you see a distorted shape. So that's how we know, but these distorted shapes, we're able to then undo these distortions because we know what galaxies look like normally if they don't have a lump of dark matter, because dark matter is smeared everywhere, but very lightly in most of the universe, and it lumps in certain places. So we have been able to figure out, once again, what dark matter actually does. And so people like me are working to figure out from this phenomenology of what the dark matter is actually doing, what its nature is likely to be. So that's a big open puzzle. So that's not solved yet. So let's kind of, fast forward to black holes. So again, in the last 25 years or so, we have come to understand and to see that nearly every galaxy in the universe, including our own galaxy, the Milky Way, harbors a central supermassive black hole. So a supermassive black hole is simply a black hole that is 1,000,000 times the mass of our sun or larger. So quite a large black hole in the center. And it appears like most galaxies harbor this supermassive black hole. They host one. So the question is, if this is such a ubiquitous phenomenon, then somehow it has to be tied to the formation of the galaxy itself. How did it get there? Right? And so that's a question that really puzzled me. And during my PhD thesis in Cambridge, I started thinking about, integrating black holes into the larger scheme of, dark matter, dark energy, and the formation of galaxies. And of course, the data has only gotten much, much better, even in the last, 25, 30 years. And I was in particular interested after I joined Yale as a junior faculty member. So my research program was focused on trying to understand the origin of the very first black holes. Because obviously the Milky Way galaxy we know as part of how structure assembles in the universe sort of aggregates and forms over time. So the universe first forms very small galaxies, small structures, which then all combine, coalesce by gravity, and then form the bigger galaxies that we see. And so the question is, when did the first black holes form, and what are the ways in which they could have formed? So there is a traditional way that Subramaniam Chandrasekhar taught us, which is that you form the first stars and they live out their lives and they leave behind a corpse, and that's a black hole. But those black holes are actually quite small because the stars are maybe 8-10 times the mass of our sun when they're born, and those are the ones that will inevitably give you a black hole at the end. And but then the black hole that's sitting in the center of our Milky Way, right, which is a garden variety galaxy, it's not a special galaxy, it's your average galaxy, and that seems to be 1,000,000 times the mass of the sun. So how do you go from a small black hole, tiny black hole that's maybe 10 times the mass of the sun, and grow it to something that's 1,000,000 or 1,000,000,000 times, right? So it takes time. And black holes grow by either feeding on gas or colliding with each other. And it turns out that the Hubble Space Telescope and ground-based telescopes were already showing us about 15 years ago that you have these supermassive black holes already in place when the universe was really, really young. So then there's a timing problem. You need time to grow these thin, light, little black holes into supermassive black holes. And the question is, how? And that's when, I started thinking about, can we just circumvent the formation of light seeds and form very heavy seed black holes that are just born massive to start with. So maybe they are born with a mass of 1,000 times the mass of the sun, 10,000, maybe even 100,000, right? And the question is, how could nature help you? Well, physics, is there physics that will allow you to make, in the very early universe, that will permit you to make these black holes? And so with one of my postdocs at the time, we were able to show that it's possible and that it could happen by direct collapse of gas. So you would have gas disks that form in the early universe that instead of fragmenting and forming stars, would, under certain circumstances, just all collapse in, cave in, and form a very massive seed black hole. And the question then is, that's a great idea, but this is science. So it has to have, does it have observable consequences? Can we actually find such objects? So, over the years, I've been working, chipping away at this problem with many of my research group members over the years. 2017, we actually wrote a paper. We figured something very interesting out. We were able to make a very concrete prediction of the kind of setting in which this direct collapse black hole would form and grow. And we realized that there's a very special time in the universe when these direct collapse black holes would be growing, and they would be harbored and hosted by a very special class of galaxies. And this would be a kind of galaxy whose light would not be dominated by starlight, but would be dominated by the gas that is falling into the black hole, en route to the black hole, before it gets completely swallowed. And this gas would actually be sped up and would be glowing really very energetically in the X-rays. So we showed that there should be a new class of galaxies in which the light should be dominated by the growth of the black hole rather than the stars that are sitting in it, which is very different from what we see later on in the universe. And so we said, oh, this should be a transient state. This should be short-lived. In the cosmic sense, short-lived in the cosmic sense, right? And then we realized that all the signatures of this object could be visible to James Webb Space Telescope because they would be very distant. And with the expansion of the universe, the wavelength of light gets stretched. So it gets stretched to longer and longer wavelengths that would therefore be infrared wavelengths. And that's the precise window that James Webb is sensitive to. So this would peer far back into the universe where we expect the first black holes to form. And then they would have this very clear signature. So we predicted that. And then, we got a gift from the universe in 2023. They found the first object. And I think there may be another one as well. And that object called UHZ1 actually satisfied all the properties that had been predicted. So that was like a real, thrilling moment.
Professor Natarajan, you just ended with, how James Webb Telescope and even Chandra X-ray Telescope, them sort of corroborating what you've already discovered is a very significant moment in, what we know about the universe. But could you tell us a little bit about how it will shape future research and, our understanding about the universe? And where do we go from here? Now that we have visible proof, where do we go from?
Yeah, so I think the idea that, nature likely makes black holes in multiple ways is kind of radical. It's something that, we had speculated, and now it's becoming very clear that nature most likely makes black holes in a bunch of different ways. And the reason that's important is black holes are suddenly ubiquitous. We seem to be finding them everywhere. Everywhere you look, you're finding black holes. So the question is that they must be very efficiently made in the universe, which means there probably are many different ways to make them. So I think where we are going next is our understanding of not just the formation of the black holes. We now know that they are instrumental in shaping galaxies themselves. And therefore, an understanding that you can make black holes a bunch of different ways also tells you that you can probably make galaxies. The formation of galaxies probably have a lot of different pathways. And that the galaxies that you form in the very early universe could be quite different from the ones that we see right around us. And by extension, all the physics that we have understood from the nearby universe, all the patterns, the correlations, and the causation, right? All of that, there's a rich phenomenology out there that could look very different. Yet, of course, all conforming to physical laws. Like, thankfully for us, right, the nature, luckily, the physical laws remain the same everywhere in the universe. But so I think what it has done is it's really kind of opened up a whole set of new astrophysical processes that we could now investigate. And of course, fundamental to the fact that black holes are shaping galaxies is that, it's also tied to the fact that, probably without the black hole in our own galaxy, the Milky Way, we wouldn't be here. Because if it had not modulated the assembly of our galaxy, we would not probably have planetary systems assembling around stars. Of course, we are far away from the black hole, thankfully for us. But I think that they fundamentally shape the properties of a galaxy, and hence, one could say that, we are here because of this interplay between the black hole and stars in our galaxy. And this is the case for every galaxy.
Professor, you have studied, between Chennai and Delhi. I just wanted to understand that, since you got into the field of astrophysics, how far has, has research in the field been? Number one. And number two, there's a lot of exciting work also happening in India around the field. So as somebody who moved from India to the US, how do you view the work that is happening here, and what has your experience been?
Yeah, so no, I was very fortunate, right, that I had all these amazing opportunities. So I did my schooling up to second grade in Chennai, and then I moved to Delhi. And I finished my high school in Delhi, and then I moved to the US at the time. I got a full scholarship. It was rare at the time to go to MIT. And part of what attracted me to leave the country is, this was the late 80s. And at that time, right, I had already gotten a little bit of a taste for research as a high school student. My father had bought me a Commodore 64 once when he went for a conference to the United States. I had that computer before, almost anybody had computers, right? So I was all kind of keyed up. I taught myself how to program, and I got a research project going with the director of the Nehru Planetarium in Delhi. So I sort of, I got hooked to research. I was so seduced by research that I wanted to be able to do an undergraduate degree where somehow research would also feature. That was not available in India at the time at all. In fact, it was not available in most universities in the United States. And MIT was a standout. They had an undergraduate research opportunities program. That's what attracted me. And the other reason I went to the US is, I have a lot of other interests. I love history, I love writing, I love literature, I love art. And I wanted to be able to take courses, and I didn't want to get totally funneled. I knew I wanted to be a physicist. That was very clear to me from a very young age. I wanted to be a scientist. And my parents are professors, so, I liked the life that they had, life of the mind, and I knew I wanted to do that. But I did want to take other courses. And that's why the American system attracted me, where you could take a lot of humanities courses. And so I think the research landscape has changed fundamentally since I left the country, of course, right? India has made great strides. There's been much more investments in basic science research. Well, of course, I think there should be much more, so I should plug that here. We should put in much more money into basic scientific research. And I think we have fantastic institutes. I'm particularly been excited at these institutes called the ICERs, which are the Indian Institute for Science, Education and Research. So one of the things that had happened, right, is that early on in India, teaching and research had gotten decoupled. So teaching was done in the universities and in colleges, and the research institutes were established separately. So the teaching faculty at universities and colleges were not necessarily research active. So this is like the German model, right? So India adopted that model early on in our scientific planning. And I think America had a different model, which is the integration of research and pedagogy, so that people who are teaching you are also active in research. And what that allows you to do, it allows you to engage and give younger people a taste of research while they are still learning the foundations and the basics, right? And the ICERs have transformed. And of course, we've had these amazing institutes, the Indian Institute of Science, Indian Institute of Astrophysics, Raman Research Institute, IUCA, so at least in astronomy and astrophysics, and of course in many other scientific fields, right? NCBS, for example. We have these premier institutes now. We have fantastic people. I just think that we need the research ecosystem is good, but I think we could easily move up a notch or two. Because we're very talented people, young people, as well as the faculty who are in all these institutions. And I think with more resources and a little bit more of a shift in mindset, because, we used to operate in scarcity, and we really now have much more abundant resources for sciences and research more generally, basic research. So I think, India has joined all these large, in astronomy, large collaborative international projects like Advanced LIGO, the 30-meter class telescope, and SKA, the Square Kilometer Array. So building upon the strengths that the Indian community has. And in some cases, like in the case of Advanced LIGO, we actually want to build, we have the technical knowledge amongst the scientists and engineers in India, and just kind of channeling that towards kind of, cutting edge breakthroughs to do with the instrumentation, and then of course the science, right? So I think the prospects are really, really bright. And I think for a young person who's now studying in India, they don't have to leave the country like me. There are many, many fantastic opportunities here. And a lot of the people who are teaching in the ICERs have all had experience abroad in different research ecosystems. And so they are bringing the best of what they've seen and what they've learned. So I think it's a very exciting time for a young person to do science in India.
Professor Natarajan, before we let you go, could you give us a sneak peek into what you do, the kind of work that you're doing now in your lab? What should we look forward to, from what you're working on?
So I think there are many exciting discoveries that are in process. So some of them I can't quite speak about because we're still writing our papers. But I think, what would be, what I can tell you a little bit about. So, I do work on dark matter as well as on black holes. So the dark matter question, right? So we have we have a standard theory of dark matter, and we believe that the dark matter that is ubiquitous in the universe is actually made of a very particular and peculiar, bizarre kind of particle. It's a particle that is collisionless, in the sense that two dark matter particles will never actually hit each other head on because they don't interact. So these particles interact and coagulate only with gravity. They have no electromagnetic forces between them. They have no charge. So two dark matter particles will kind of graze around each other and eventually kind of coalesce. And then they grow by gravity. So it gravitationally aggregates dark matter. So that's the nature we believe at the moment. So we've recently, over the last couple of years, we have seen some very interesting observational data with this lensing, with the sort of bending of light by dark matter. We are seeing that the regions of the universe that have dark matter, that are causing the deflection of light, the distribution of dark matter in those regions is actually a lot more heaped than we believed. So we thought it was sort of lightly smeared, and we now see that they're actually very tight heaps and like very strong heaps of dark matter. And these heaps of dark matter, there's so much aggregation that you probably couldn't have aggregated that just by gravity. Probably need something else going on. So possibly some additional kind of interaction between these particles, dark matter. So we are seeing some emerging evidence from the data. So this is not, unlike the black hole, the ideas on black holes where, I started out making a theoretical prediction and that getting validated. Here we are going in the other direction. We're actually letting the data take us and show us, what more information we could glean about the nature of dark matter directly from observational data. And we're seeing some intriguing kind of signatures that, it remains to be seen whether this holds up with a lot more data. It has to be validated with many more observations. But I think we are starting to see something very exciting, possibly opening up in our understanding of dark matter. So I'm very, very excited about that.
And we are excited and looking forward to more of great discoveries coming from you and your lab, Professor. Thank you so much for speaking to us. And thank you to our viewers for tuning in to this interview. This was Soumya Pillai. Behind the camera was video journalist Varsha Kaur.